Hey there, STEM chemistry students. This is Miss Ruark. This is podcast 8.5, and we're going to talk about colligative properties. All right, so a colligative property. Yes, we get to start off by writing it. Yay! Colligative properties are properties that deal with the number of particles that are dissolved in a given mass of a solvent. So this is just appropriate that we talk about it now when we're in solutions, right? All right, so the physical properties of a solution differ from the properties of the actual solvent. Okay, so we could have water as our solvent and we could put, let's say, sodium chloride in it. Well, the solution is now salt water. It's a saltwater solution, and so those physical properties are going to differ from the physical properties of just the water. All right, so there are different ways that these can differ. One of those ways is through vapor pressure. By changing and adding sodium chloride to water, we can actually lower the vapor pressure. So we could do a vapor pressure lowering. We can, by lowering the vapor pressure, we can actually elevate the boiling point, or the temperature at which this subject is going to actually start to burn. And we can depress or lower, we call it depressing, the freezing point of a solution as well. You see these all the time. Let's think about it. When you go to cook spaghetti, or when you go to cook any type of noodles, or if you're going to boil potatoes, right? You probably add a little bit of salt to your water on the pot, in the pot. The reason that you do that is not, and I know you've probably heard this, it's so that it cooks faster, boils faster. Not really. What it's doing is actually you're changing, once you add that sodium chloride or that table salt to that water, you've now changed it. It's not water anymore. Water boils at 100 degrees Celsius, but when you add that sodium chloride, it's actually going to slightly elevate that boiling point of the new solution. And so now it's going to boil at a higher temperature. Right? You also see this if you lived in the north, or if you've seen anything about those ice storms and they have all those big trucks out that take around the salt. They call them salt trucks. And they go around and they deposit salt onto the road to keep the water to keep the snow from sticking. It also helps to keep any water that's on the ground from forming into ice once the temperature drops and it becomes nighttime. Okay, so they do that because they're depressing or lowering that freezing point by adding the salt to the solutions. Okay, so colligative properties. These are properties of solution that depend on the number of solute particles dissolved in the solution. Okay, so you're going to hear that a lot. It's the number of particles in the solution that determine these colligative properties. It's not the identity of the particle is not important. The size and the molar mass is not important. What's important here is the number of solute particles that determine the colligative properties. Okay, and we're actually going to use molality. We just learned this one too, right? Molality, which is moles per kilograms, moles of solute per kilograms of solvent. Okay, and that's what we use to determine these colligative properties, how much the boiling point goes up and how much the freezing point goes down. And you've seen this before, so I'm going to keep moving. All right, so vapor pressure lowering. The pressure exerted by a vapor that is in a dynamic equilibrium with its liquid phase in a closed container. Okay, so that's the vapor pressure. We all know this. We've talked about this several times now. All right, well, when solutes are added to a pure solvent, the vapor pressure is going to be lowered or decreased. Okay. Less solvent molecules will be able to escape the liquid phase. Now, down on the bottom of your paper, there's a thing that says sketch, so you can sketch this in there if you want to. I think I'll have place to do it right here. All right, so here is our beaker. All right, and it's got our solvent in it. Here's our solvent. Water molecules all over the place, right? Water's the easiest one to use. Okay, well then we take this other substance and we add it in. Let's say we put sodium chloride in here. All right, so these sodium chloride molecules are now floating around in here as well. And you notice how these sodium chloride molecules, the sodiums and the chlorines, because when we put sodium chloride, it's an ionic compound. When we put an ionic compound, excuse me, into water, it dissociates. Okay, and that's when we were determining our solubility rules. We said it was aqueous or we said it was a solid. If it's aqueous, it is soluble in water, which means it's going to dissociate completely. So it'll break apart into the ions that make it up. So we've got sodium and chlorine ions in here, and these water molecules are trying to escape. They have to be close to the surface so they can escape and become the vapor pressure up here. But guess what? Some of them are being blocked and they can't get through. Okay, so what's happening here is it's blocking them from leaving, and it's going to lower that vapor pressure. All right, so how much will it lower it? Well, the decrease is proportional to the number of solute particles that are dissolved. All right, well, let's talk about that. Okay, here we have glucose, we have sodium chloride, and we have calcium chloride. All right, glucose is not an ionic compound. Glucose is C6H12O6. All right, glucose is not an ionic compound. It is a molecular compound. It's a molecular solid. So it is actually, when it goes into water, when it dissolves into glucose molecules. They stay together. They don't dissociate. And so when we talk about them going into water, one molecule of this stays as one molecule in that water when it's dissociated or broken apart. It doesn't break into its ions because there are no ions. All right, well, here we have sodium chloride. Guess what? Sodium chloride breaks apart into sodium ions and chlorine ions. So it dissociates into two substances, two things, and so it would be dissolved and it would break apart into two different things. Okay, well, look, we've got less particles here than we do here. All right, well, calcium chloride, ionic again, it's going to break apart into calcium with a positive 2 charge, but guess what? It's also going to have two chlorine ions. One here plus two here gives us a total of 3. And so this one is going to have more numbers of solute, and so this one is actually going to affect that vapor pressure more than the sodium chloride, which will affect it more than the glucose. Okay, so based on the number of particles, the glucose has the least impact. The calcium chloride has the greatest impact on lowering that vapor pressure. Okay, vapor pressure decreases. Okay, so it's going to excuse me. Vapor pressure decreases when a non-volatile solute is added to a solvent. Okay, so a volatile substance is something that does not want to stay in the liquid phase. It prefers to remain in the gaseous phase. So it will automatically evaporate on its own. So if it's a non-volatile, it's not going to evaporate on its own. Okay, so vapor pressure lowering is going to be directly proportional to a solution's concentration. Okay, concentration. So that means the more you have in there blocking the particles from evaporating, the lower the vapor pressure will be. All right, so how does it affect boiling point? Well, if you lower the vapor pressure, you're going to elevate the boiling point because elevation. When a solute that dissociates is added to a solution, the boiling point of the solution will increase. Okay, because, well, we'll get to that in just a second. Just remember that boiling point is the temperature where the vapor pressure of the liquid equals the atmospheric pressure, and that's the only way that it can boil. And so if you lower the vapor pressure, you're going to have to increase the temperature so that it will boil. So it's going to have to boil at a higher temperature so it can get that vapor pressure back up. All right, so when solute is added, so when we add solute to a solvent, the vapor pressure is going to be lowered. So the temperature, the boiling temperature, the temperature at which it's going to start boiling will have to be higher or elevated. What we have to do is add additional kinetic energy so that we can break apart the solute-solvent interactions, those IMFs that are in there holding them together, so that we can overcome that atmospheric pressure and allow it to boil. All right, well, temperature difference between the boiling point of a solution and the pure solvent depends strictly on the number of solute particles. Look, we heard that again. Must be important. Okay, the number. Doesn't matter on the identity, the mass, or anything else like that. All right, well, we do have this funky equation that you need to know. I think it's in here. Did I leave it in here? No. All right, so my equation is delta TB, which means the change in the boiling temperature is equal to KB times M times I. All right, so this right here, this delta T is the change in boiling point temperature. KB is a constant for the solvent. I is what we call a Van Hoff factor, which I'll tell you about in just a minute. And M is the molality. Okay, this is something that we can use to show, if we needed to, we could actually go backwards and figure out what the molar mass of the substance is if we needed to, but I don't think I'm going to make you do that. All right, so this occurs because additional solute particles lower the vapor pressure, so more pressure is needed to boil, and more energy is needed to break those intermolecular forces and exert that additional vapor pressure. I'll show you how to use this in just a minute. Oh, I had it on there. All right, so I, that Van Hoff factor, I is what we call the dissociation constant or factor. Okay, so it talks about the number of particles into which the solute will dissociate. All right, so how does this work? Well, we just talked about it a little. For all molecular compounds or covalent, the Van Hoff factor will always be equal to 1 because they don't dissociate. For ionic compounds that are strong, the ones that produce aqueous substances, the Van Hoff factor depends on the number of particles that dissociate. So what does that mean? Well, that means that sodium chloride will break apart into Na and Cl. And so our Van Hoff factor would be 1 Na and 1 Cl. 1 plus 1 is 2. Well, that's so easy. I know, right? Let's do another one. All right, what if we have Na3PO4? Well, we end up with 3 Nas plus 1 PO4, so our Van Hoff factor would end up being 4. Hopefully you got that. If you didn't, just let me know when you get to class. We'll go through it again. All right, freezing point depression. We're almost done. Hopefully I can get these examples in. Temperature difference between the freezing point of a solution and a pure solvent. What happens is the solutes will come in and disrupt the normal geometric pattern of a pure frozen solvent in a solution and keep it from allowing it to become that nice pretty lattice. So it won't let it form the crystal lattice because it's disrupting it. So this solution will, the solvent will actually stay in solution instead of crystallizing. You need additional kinetic energy in order that needs to be pulled out to allow that solidification to happen. And the example or the equation that we have here is delta TF. So that's the change in the freezing point temperature. KF is the constant, M is the molality, and I is that Van Hoff factor again. And I said this earlier, delta, the change in temperature for freezing and boiling point, can be used to find the molar mass of a substance if we really needed to, but I don't think I'm going to make you guys do that. All right, so here is a page with constants on it. I'm going to have a copy of this for you when you get to class tomorrow so that it will be yours to keep. Yay, don't lose it. Okay, so here's some examples. I'll try to get through both, which means I'm going to have to go kind of quick. All right, if I can't get through the second one, I'll get through the first one and then we'll do the second one in class. So it says a solution is prepared by dissolving 4.9 grams of sucrose, here's the formula for sucrose, in 175 grams of water. Calculate the boiling point of the solution. And they say sucrose is a non-electrolyte. Now, we haven't talked about that. That just means that sucrose does not dissociate, does not break apart. That means that it is molecular. So it's going to have a Van Hoff factor of 1. That's all they're telling you. Okay. When we look at our chart, our Kb value, let's go back. Our Kb value for water is 0.51. Okay, so we know that Kb is equal to 0.51 and it's degrees Celsius times kilograms per mole. Excuse me. We're looking for the boiling point, so we've got to find delta T, and our molality, we would have to take 4.9 grams of sucrose, and we have to change it from grams to moles. And I'm going to run out of time here, so I do apologize. I can finish it in class for you, though. Okay, so 342.34 grams per 1 mole, and that will give us, how many moles? 0.01431 moles. We use that to find our molality, okay? And our molality would be this changed into kilograms. That gives us our molality.